now.
Hello everyone and welcome to our YouTube channel. We are working on a series of videos on CUDA. So on the past few weeks, we have been making videos on parallel computing by using multiple software. And this time we will be discussing CUDA. So previously we discussed OpenMP and MPI, both of which primarily works on the CPU. And now we are moving to a new API, which is called CUDA. So what exactly is CUDA? CUDA is a parallel computing software since that's what we have been discussing for the past few weeks. It is another type of parallel computing software. But the difference from OpenMP and MPI is that CUDA was developed by NVIDIA specifically for NVIDIA GPUs. So you can use the power of the GPU to perform calculations and simulations, which was previously restricted to just CPU. So one more question. So people can ask like, why do we need to shift from the traditional to a GPU computing program at all? So the major difference between any CPU program and a GPU program is that, so CPU, basically the difference between the two architectures is that CPU has a very limited number of resources. So by limited, what I mean is that uh, so a CPU generally ranges from 4 cores to 128 cores at max. But GPU starts from 128 cores generally and go all the way up to 60,000 cores. So that is a very large difference between the two architectures. And because of the higher number of cores, you can launch multiple simultaneous tasks on GPU, which is not possible on the CPU due to hardware limitations. So let's get right to the program. And as in the case of any programming language, the first program that we study will be Hello World. So what are the additions here? So Hello World is a very simple. I think almost everyone is now familiar with Hello World. So what's the difference in CUDA? First, we'll need to assign a global variable. So I have defined this, I have written this global here and void CUDA. So what does this global mean? Global means that this variable, that means CUDA hello, will be run on the GPU. That is what global defines. So whatever is inside this inside this bracket will be executed by the GPU. Then I have the main function, so int main, and here I am launching the kernel. What exactly is the kernel? Basically, I am launching this function, and since it's not a normal function, it's a CUDA function. So that's the syntax of how you launch the function. And what are these numbers if you ask? I will clear them in the live demo. And next we have CUDA device synchronize. So that means what does this do is synchronize the CPU and the GPU so that there are no back delays. So what's happened is, because the entirety of the program is being run by the CPU, only this function will be executed by the GPU. So there can be some delays between the two since GPU is a separate entity from the CPU. There can be delays. So this function ensures that there is no such thing and the program works perfectly. So let's go right to the live demo. So here is the program. We will execute this program. So uh, first of all, let's just keep it at 1.1 right now. And I just want to give you a demo of this. So to run any CUDA program, first we'll need to load some modules. So right now I'm loading SPAC. And then SPAC is basically a management software. And then I can do SPAC load CUDA. So CUDA by default is not loaded on the system. You need to follow this procedure to load it onto the system. So I'm going to copy this code and just paste it here. Yeah. So it's giving me a few warnings, but it's fine. So now, since I have loaded the module, I can get to compiling it. This is the program that I will compile. So CUDA we'll have to use the CUDA compiler. It's nvcc and hello world. That's the file name using cuda.cu. Cu is the file extension for any CUDA file. So do cc+1. Okay. So it needs GCC as well. No worries. So this exception was arise because GCC was not loaded. Actually, there is some issue on the system that I'm working on. So this is the HPC param rudra, and here HVCC and GCC are not linked. I think for certain modules this issue exists. So that needs to be resolved, and let's just use this one. I think it should work fine. Let's clear the screen. And then I can compile again. It's taking some time to compile. Oh yeah, now it's compiling. I forgot to add that currently I'm in the GPU node of the HPC. Basically, the node that has a GPU. So not all nodes inside this HPC has a GPU. So you need to log into the specific node for this program to work. So since the program is compiled, let's check the output dot slash a dot out. Yeah. Hello world from supercomputer GPU thread 0. So that is what I've written here. So let's leave it like that. And let's discuss this. So I had left it out that I'll explain it later in the video. So let's talk about this. What are these? So these are called threads and blocks. So basically what I mean to say is whenever I write a CUDA function, let's say CUDA, just for reference. So I need 3 less thans, and then there is block, comma, thread, 3 greater thans. So block, comma, thread. So what do I mean by that? This is a special type of categorization inside of CUDA. So thread is like a normal single worker that we have studied in the previous videos as well. Very similar to that we have done in the OpenMP videos. It's a single worker executes a single task. Block is a combination or like a collection, community of threads that are connected to each other and can share data between each other. So I can have, let's open something. Okay. So inside of a block, I can have, let's say 10 threads, and those 10 threads will be part of a single community and can share data between them, and they are independent from the threads in other blocks. So there is no sharing otherwise said explicitly. So this is what the system is, blocks and threads. It's a pretty new concept, and it's a pretty tough concept when we go to more complex problems. This is a problem. This is something that needs to be understood properly. Okay, for now, let's try changing the number of threads to 30 and see what happens. I'll just compile the program again and then run it. So now I've got output from 30 threads. Basically, so how many numbers I can put here, and I will get that many replies from the system. That it will execute the program that many times. So because thread is a single worker, so I have launched 30 threads. All of them will perform this task since I have not specified which thread I want to perform the task from. Okay. Similarly, for blocks, I can deploy multiple blocks since it's a simple program. The concept of blocks and threads is can feel like a little obscure right now, but when we move to more complex problems, specifically vector addition and matrix multiplication, there this block and thread method becomes much more clear. So that is it for this video. Thank you for watching.